Very good
Very good
afternoon.
afternoon.
I thank
I thank
I thank Principal Director Sir of this institute and the coordinators of this MTP for inviting me to deliver this lecture over here today. So I have kept my presentation very at the introductory level. I have discussed about polymers, then composite materials. Then I will be showing some portions of the work which my students have done. So I will be starting with, because the presentation is based on nanocomposites, so I will start by defining what the word nano means. So actually the word nano is a Greek word, and its meaning in Greek, or if we translate it to English, its meaning will be dwarf. So something which is very small is called as nano in Greek. So in present context, because we are doing research on nanomaterials, so in our present context, the word nano will be standing for a prefix. Prefix means it will come in front of some other word. So it is a prefix and it will mean 10 to the power minus 9. So if you say nanometer, then it will mean 10 to the power minus 9 meter. So it will be 10 to the power minus times of a, by 10 to the power minus 9 times of a meter, or 1 billionth of a meter. So a nanometer is therefore 1 billionth of a meter. Therefore, what is the nanoscience? So nanoscience is therefore the science which will deal with the study of atoms, molecules and nanoparticles which are in the nanoscale. So there is a specific length scale which is called as the nanoscale. I will discuss shortly. So nanoscience will be dealing with the study of atoms, molecules and other particles which are in the nanoscale. And in the nanoscale, it is not that all dimensions should be in the nanoscale. If at least one dimension of a material is in the nanoscale, then we can call it as a nanomaterial. Okay, so here I have given some examples of nano sizes. See, I have started with an atom. You know, atom is the basic unit of a material. So size of a carbon atom is almost 0.15 nanometer in diameter. So diameter of carbon atom is it is not exactly 0.15, but it will be almost 0.15 nanometer in diameter. Then after atom, let us look at a molecule. Water molecule, it will be 0.3 nanometer across. Across again will mean the diameter. So in a water molecule, how many atoms are there? If I ask how many atoms are there in a water molecule? It is H2O, is not it? So there is 2 hydrogen atom and 1 oxygen atom. So the collection of all 3 atoms together constitutes the water molecule, and it is 0.3 nanometer in diameter. Again, after molecule, let us look at a cell. It is one example is the red blood cell, which is almost 7,000 nanometer wide. You know, the cells are the basic units of the organisms, human and all other organisms. So red blood cells, which are the cells of the blood, they are almost 7,000 nanometer wide. Now our human hair is almost 80,000 nanometer wide. Okay, so we know how much we every day look at maybe one single hair we always find. So one single hair will be almost 80,000 nanometer in diameter. So this is a slide which I have taken from the book Science at Nanoscale. It is there mentioned in the references. So here the nanoscale in a comparative scale, what nanometer is about, that is described. You see at the corner, that is human hair, that it is almost 80,000 3000 nanometer, or we can say it is almost 100 micrometer in width. So if you make 100 slices, it is not possible, but suppose we are taking one single hair and we are making vertically 100 slices, not horizontally but vertically. If you make 100 slices, and out of those 100 slices, if you take one slice, and out of those one slice, out of that one slice, if you again make it into 1000 slices, and out of those 1000, if you take one slice, that will be almost equal to 1 nanometer. So I have kept this figure or diagram so that you all can have an idea that how much small 1 nanometer is. To see the width of one hair only, it is very difficult. And that one hair you are first making 100 slices. I am again repeating, not horizontally but vertically. In this direction we are making 100 slices. Out of those 100 slices we are taking one slice. And one slice again we are making 1000 pieces or slices. And from those 1000 slices, if you take one slice, that will be almost equal to 1 nanometer. So 1 nanometer is something which is very, very small and we cannot see with our naked eye. So after nano size, the next term which goes along with it is the nanotechnology. So actually nanoscience is the study of atoms and molecules at the nanoscale, and nanotechnology actually is the application area of nanoscience. So our nanotechnology refers to the fabrication of nanometer sized materials which will be in the scale of nanometer and which will be called as nanomaterials. And it is not that you make it and then you do nothing out of it, but technology will mean that after you make the material, you have to put it into some good use. And therefore it is written to make good use of the improved physical, chemical and biological properties, so as to develop superior materials, engineering processes and systematic products. So why it is said improved physical, chemical and biological property? Because at the nanoscale, the properties of the material which it had been exhibiting at the macro scale or at the bulk scale, those properties gets changed. Most of the materials shows changes in their properties. And it is not that physical, chemical and biological properties will change. All different properties like thermal, electrical, magnetic, mechanical, different properties will undergo changes at the nanoscale. And these improved properties are made use of to discover new materials which are nowadays finding uses in different areas. So nanoparticles are actually the building blocks of nanotechnology. So what makes nanotechnology? The nanoparticles are the units of nanotechnology and they are the building blocks of nanotechnology, and the dimensions are in the nanometer scale, that is 1 to 100 nanometer. So this is where I want to explain, like any length scale can be converted to nanometer scale. Suppose I take 1 nanometer. So 1 nanometer can also be 1 meter, 1 meter can also be converted to nanometer, right? So because 1 nanometer will be 1 billionth of a meter, so 1 meter will be 1 billion nanometer, is not it? So 1 meter also you can, okay. 1 meter will be equal to 1 billion nanometer. So so 1 meter is something which is visible. 1 meter to ami dekha pai thaku, but 1 nanometer ami dekha pam jano napam, but 1 nanometer ku ami 1 meter ku ami nanoscale likhisu. So the thing is that the particles will exhibit different properties only when they are in the scale of 1 to 100 nanometer. Okay, not 1 meter, 1 kilometer like that. So the particle sizes, particles are what? They are the constituents of the material. the particle sizes should be in the scale of 1 to 100 nanometer. So the materials will be visible to us. Material bilak ami dekha pam, kintu hiyotor particle bor ami dekha napam. The particles are in the size scale of 1 to 100 nanometer. So as to observe the particles, you have to take some high precision instruments and take the images of the particles. Now nanoparticles, as I have said, they should be in the scale of 1 to 100 nanometer, and they can be metals, they can be semiconductors, insulators. So similar to bulk materials, they can have metallic, insulating, semiconducting, all different kinds of properties. Now when the dimensions, like in the first point only I have written that when the dimensions are reduced to the nanoscale, the properties changes. So the materials suddenly show very different properties compared to what they exhibit on the macro scale, which enables unique applications. So আজিকালি যে ইমান nanomaterial nanoparticle বুলি সবৰ মুখে মুখে আমি শুনি থাকো যে nanotechnology use হৈছে, nanomaterial use হৈ আছে, হয় নাই? So all the electronic devices nowadays are little bit different from what they were few years back. So because of the use of nanomaterials, but why the nanomaterials are being used? Because at the nanoscale the materials shows different properties, and some properties may be very unique in the sense like no other materials can exhibit such properties. So this enables unique applications. The changes or the new properties which comes into existence, they results in the different applications of the material. Now since I work on semiconducting materials mostly, so I have kept this slide on semiconducting nanoparticles. I said that nanoparticles can be metals, they can be insulators, and they can be semiconductors also. Now in the recent times, the semiconducting nanoparticles are receiving immense applications in different areas. And this is why, because they exhibit some unique properties which are not exhibited by the bulk material. The same material, when in the bulk scale and when in the nano scale, they will exhibit different kinds of property. And this is particularly true for semiconductors which are belonging to group 2,6. Now you may ask what is group 2,6? I have kept one slide for that. After some slides here that will come, I will explain there what group 2,6 means. So semiconducting materials such as group 2,6 semiconductors such as cadmium sulfide, zinc sulfide, these are mostly studied by researchers, and we have also studied. So such semiconductors finds applications in fields such as electronics, optoelectronics, nonlinear optics, and many other. These four are not the limitations. There are many fields where the semiconducting nanomaterials finds application. Now semiconducting nanomaterials, they exhibit some important features, like these three important features I have listed at the bottom of the slide. That is large surface. Okay, so why that huge surface area comes into existence? Is it okay to all of you, or should I need to explain how surface area increases? বুজাব লাগিব নেকি surface area to কেনেকৈ বাঢ়ি যায়? বুজাই দিও অলপমান মানে বুজাই দিছো। So surface area, suppose this is a pen which I am holding. এই গোটেইবিলাক ইয়াৰ surface, everything or all parts which is in contact with the environment is its surface, okay, and it is having a particular volume. The material is having some volume. Suppose I break this pen, exactly at the center I break this pen. Then কি হ'ব? এই যোনটো লাইনেৰে মই ভাঙিলো সেইখিনিতে দুটা নতুন সারফেস ক্রিয়েট হ'ব। যোনকিটা সারফেস নেকি প্ৰথমতে এতিয়া ভিতৰত আছে, সেই দুটা সারফেস এতিয়া বাহিৰলৈ ওলাই আহিব। তাৰ মানে এইটো পেনৰ যদি মই দুটা ভাগ কৰো, এইটো ভাগৰ লগত এটা নতুন সারফেস আহিব, এফালৰ ভাগটোৰ লগত আনটো নতুন সারফেস আহিব। Can you get it? What I am explaining? বুজি পাইছেনে? So once I break it, two new surfaces are getting produced. But if you take the two pieces together and calculate the volume will remain same, like the volume it had initially. Now out these two pieces, suppose I take one more piece and I break it once more, then from that other piece, two more new surface will form. Okay. Again from the other piece, two more new surfaces will form. So at first it was one pen. Now out of the two, when I break it once, two new surfaces are created. When I break it twice, four more new surfaces are created. Likewise, if you repeatedly go on breaking it, there will be many number of new surfaces which are created. So, but the thing is, if you collectively take all the surfaces, then all the pieces actually, then the volume will remain the same. So in comparison to the volume, the surface area of the nanomaterials goes on increasing. So at a point of time when you go on breaking, the what will happen? The picture will be such that most of the atoms will lie at the surface. So the material will have a huge surface area, and its volume will be the same as it had initially. Again, the band gap. You know, band gap is the distance in energy between the bottom of the conduction band and the top of the valence band in a semiconductor. In a semiconductor, the energy separation between the top of the valence band and the bottom of the conduction band, that is called as the band gap. Now, when the material is converted to the nanoscale, the band gap gets enhanced. So with reduction in particle size, the band gap gets enhanced. So if you take a particular semiconductor in the bulk scale, and from that bulk scale you make the nano material out of it, then the nano material will possess a higher band gap and compared to the bulk material. But what is the meaning of word tunable? Means you can keep on changing the band gap. How you can keep on changing the band gap? If you prepare a nano material which is having 90 nanometer particle size, then it will have one value of the band gap. If you take or prepare one more nanomaterial with 50 nanometer particle size, then its band gap will be again different from the 90 nanometer size. So when the sizes of the particles keeps on changing, the band gap of the material also keeps on changing, which means smaller the particle size, greater will be the band gap. So you can tune the band gap. Tuning, you know, when you are matching the frequency of your TV channels with the frequency of the broadcaster or the telecaster, from where the channels are being telecast. That frequency you are matching with the frequency of your television set of your home. Then you are saying that I am tuning. Tuning is to match. So the band gap can also be tuned. You can either increase it or you can decrease it according to the sizes of the particles which are formed. The quantum confinement is another phenomena which is being exhibited by semiconducting nanoparticles. Like in the bulk scale, the charge carriers of the material, charge carriers are electrons and holes. In the material, the charge carriers are electrons and holes. And in a bulk material, the electrons and holes are able to move in all the three dimensions. But in the nanomaterial, the charge carriers will be restricted to move in either one dimension or two dimension, or altogether three dimensions they will be unable to move. So in other words, that restriction is saying that the materials are confined. They are confined, they are not able to move. Okay, so the proper word is quantum confinement. Why the word quantum has come? Because at the nanoscale, classical physics cannot explain the concepts. We need the help of quantum physics. That's why the word quantum is associated with the word confinement. So these are three important properties or features which semiconducting nanoparticles exhibit. Now when I said that there is a phenomena called quantum confinement, the structures which are formed are called as low dimensional structure. See, the three-dimensional structures where the charge carriers are able to move along x, y, z, all three dimensions, they are not low dimensional structure. But the structures where there is confinement of charge carriers. Sometimes the charge carriers are confined along one dimension. That type of structure will be called a quantum well. Charge carriers are unable to move along one dimension. They are free to move along two dimensions. Such a structure is called as a quantum well. Then when the charge carriers are free only along one dimension and are restricted along two dimensions, such a structure will be called as a quantum wire. And when a structure is such that all the charge carriers are unable to move, they will be confined at one point of space. That kind of structure will be called as a quantum dot. Dot because all charge carriers are confined at one point. So it is a quantum dot. Again, the word quantum is associated because quantum mechanics is needed to explain the concepts of these quantum structures. So all these structures, quantum well, quantum wire, quantum dot, these are called as low dimensional structures. Okay, so in these low dimensional structures, there is also one new thing which emerges, that is the energy levels gets changed. The energy levels which the bulk material will exhibit at the nanoscale or at this one-dimensional, two-dimensional or three-dimensional scale, zero-dimensional scale, the energy levels will get changed, and this is its representation. See, at the extreme left, the structure which is drawn is a bulk material or a three-dimensional material. That is not a nanomaterial. The 3D bulk, it is written, no? That is not a nanomaterial or that is not a low-dimensional material, but it is a three-dimensional material where the charge carriers are free to move in all dimensions. But the second structure you see, it is a quantum well, and it is a two-dimensional structure, which means the charge carriers are able to move in suppose x and y dimension, but it is unable to move in the z. So along one dimension it will have restriction, and it is a planar structure, like a plane. It will have only two dimensions. Then the third structure is the quantum wire. You can see how the quantum wire looks like. That is one-dimensional structure. The common examples are the carbon nanotubes. These are tubular structure, no? Then zero-dimensional structure is the quantum dot. Now in this figure, the energy levels are not directly drawn, but the density of states are drawn against the values of energy. Density of states is what? It is the number of energy states per unit volume in a material. Number of energy states per unit volume in a material, that is called as density of states. So that density of states for a bulk material, at the lower line if you observe, for a bulk material the density of states, that is giving a continuous curve. It is a continuous curve. However, for the next figure you see, there is a staircase like figure which has emerged. For the, that is the two-dimensional case. For the one-dimensional case, you see some broken line kind of structure has come, or energy levels have come. And for the quantum dot case, all the energy levels are discrete. Okay, so that continuous structure is absent in case of low-dimensional structure, or the continuous nature is absent in case of low-dimensional structure, and the energy levels becomes, or the energy level diagram becomes discrete. Discrete means one is not connected to another. Something which is not continuous is called as discrete. So this is the variation of density of states in different structures. Now, because my topic is polymer-based nanomaterials or nanocomposites, so I will be discussing what a composite material is. So if you have anything to ask up to this last slide, you can ask. If anything is there, kiba hudibo bisarile hudibo pare. Okay, then let us see what composite material is. See, many of our recent or modern technology that will need unusual combination of properties which cannot be met with by conventional metals, alloys, ceramics or polymeric material. So the naturally available materials might not be able to give some performances which we nowadays need in our recent devices. For example, a very simple example is our vehicles which we drive or run nowadays. The vehicles which are running nowadays are quite different. It is full of electronics, is not it? Azikali notun gari, bike, teneka bilak, it's full of electronics because see, different semiconducting materials are finding use there. The vehicles I am only taking as an example. There are many other examples to give. Nowadays, because of high prices of fuels, we need vehicles which will be light in weight so that it will consume less amount of fuel. We need vehicles which will be lighter in weight and will run with lesser amount of fuel. For that, you will have to prepare the vehicle's body with a material which will be not a pure metal like in the previous time. It will be prepared with some composite material. Only when you use a composite material, you will be getting all the performances you are in need nowadays, not in case of vehicles. For vehicles, we need a body which will need very less fuel for running less distances, so that it has to be lightweight. And lightweight does not mean that it has to be very weak. It has to be strong also. So different combination of properties like our mobile phones. Mobile phones are using so many different kind of applications in it. So these applications were not possible with the previous days material. So we need newer kind of materials so as to fulfill the different kind of needs which we require nowadays. For example, the electric fans which we have nowadays. These fans are very lighter compared to the fans which we had few years back. Not few, maybe 10-20 years back. Okay, these fans, they are doing what? They are running on less amount of electricity. Power requirement is less. So the body of the fans nowadays is prepared with such a material which will be lighter in weight. So we cannot say that these are all single element material. These are actually composite materials which are used nowadays. So it is said that there should be unusual combination of properties that cannot be met by conventional materials like metals, alloys, ceramic or polymers. These are all conventional materials which has been used for a long time. So this is true for materials which are needed for aerospace. This is only as an example. The aerospace area is mentioned here. So materials which are needed for aerospace, underwater and transportation application along with a host of other application. Transportation already I have said. Our modern day vehicles, buses, all these are little bit different from what it was many years back. Then the aeroplanes, the underwater marines which are used, all these kind of applications are running on composite materials. Let us look at the aircraft. For an aircraft, we need material which will have low density. The material has to be strong. The material has to be stiff. The material has to be abrasion and impact resistant. And all these properties, along with it, it should not get corroded very easily. So while building an aircraft, you need all these kind of properties. The body of the aircraft should have low density, it should be strong, it should be stiff, it should be resistant to abrasion, it should be resistant to impacts. Then it should also not get corroded easily, because while flying at high altitude, it may encounter different atmosphere. So all this combination is not possible. Combination of properties actually is not possible with our normal conventional material. So combination of properties is possible by the development of what is called as composite material. Okay. So then what is a composite material? It is actually a multi-phase material. where that exhibits a significant portion of properties of both the constituent phases. So there will be two or more than two phases in it. Phases actually does not mean that it will be solid, liquid like that, but it will have different phases, means it will have different particles embedded with some other matrix material, which we will discuss now. So a composite is a multi-phase material which exhibits a significant proportion of properties of both the constituent phases, such that a better combination of properties is realized. And such a combination of property is obtained by combining two or more distinct materials in definite proportion. So you will have to combine two materials or more than two materials together in a definite proportion or ratio, so as to get a composite materials. So composites again can be alloys, they can be ceramics, they can be polymer. And in the present context, the composite is a multi-phase material that is artificially made. You will not get composites naturally, although there are few natural composites also. But in the present context, the composite which we are discussing, that is artificially made, in contrast to the one that occurs naturally. Also, the constituent phases must be chemically dissimilar. There should be two different kind of materials forming the composite and separated by distinct interface. There should be well-defined boundary between the two phases, which means there should be a distinct interface. Therefore, in designing composite, scientists and engineers have combined various metals, ceramics and polymers so as to form new generation of extraordinary materials, which will possess different properties, which are enhanced properties like stiffness, toughness, high temperature, strength, all these. These are all better properties. Now, many composites are composed of just two phases. In many composites, there are only two phases. One of those phases will be called as matrix, which is continuous and surrounds the other phase, which is called as dispersed phase. Okay, so when we say nanocomposite, it also means that it is a combination of two different materials or two different phases. So the properties of the composite are a function of the properties of the constituent phases. So when you make the composite material, the final property which the material will be exhibiting, that will be a part of properties of both the material. It will be a combined property of both the individual phases and their relative amount. কোনোবা এটা phase বোলে বেছিকে আছে, কোনোবা এটা কমকে আছে, the final property will depend on the relative amount also. In one composite, if you take one material in larger amount and the other in smaller amount, then its property will be different from one more material which will have different amounts of the two material. So geometry of the dispersed phase also determines the properties of the composite. Geometry includes shape of the particles, its size, distribution and orientation of the particles. So I have drawn some figures so as to so that you all are able to follow what I am speaking. Okay, so these figures, you see various geometrical and spatial characteristics of dispersed phase particles. You see that pink color portion within the blue boundary, the pink color portion which I have shown, that is the matrix. The matrix is continuous, which means it is spread throughout the material. And inside the matrix, there will be the dispersed phase particles. Those blue color arrows, this is just a notation. This is just a notation which I have used. The blue color arrows are denoting the dispersed phase particles. Dispersed means they are embedded within the matrix. So, what is the distinction between the top two figures? Okay, in the left hand side figure, the number of dispersed phase particles are less. And in the right hand side figure on the top, the number of dispersed phase particles are more. Which means the concentration of dispersed phase particles is lesser on the left hand side figure at the top, and the concentration is more on the right hand side figure at the top. So what I am wanting to say is that the final property of both these composites, although both are the same composite, matrix to একে আছে, particle embedded particle to একে আছে. Suppose the matrix is some polymer and the particles are some metals. So in the first case, the final property of the composite will be different, and in the second case also the final property will be different. But what is bringing the difference? The concentration of the embedded particles. So concentration of the dispersed phase particles, that changes the properties of the composite. In the second case, you see size. In the bottom two figures, on the left hand side figure, the size of the dispersed phase particle are little bit smaller, and on the right hand side figure, although the dispersed phase particles are 2, but their sizes are bigger. So the sizes of the dispersed phase particle will also change the property of the final material. Okay, so is it বুঝি পাইছে না কথাবোৰ? Is it clear, or do I need to explain it again? So what I am saying is that here I am discussing a composite with two different materials, the embedded material and the surrounding material. The surrounding material is the matrix, the embedded material is the dispersed phase particles. So we are here, we have seen that concentration and size of the dispersed phase particles affects the final properties. After that, you see the shape. In the two figures on the top, the shape, it is just a representation which I have drawn. The shape of the particles are different. Although the same number of particles are there, the shape of the particles on the left hand side figure and on the right hand side figure are different. So that shape also determines the final properties of the composite material. Then distribution. In the bottom figure on the left hand side, the distribution is continuous, and in the right hand side figure, the distribution is little bit not continuous. So the distribution of the embedded particles or dispersed particles, that will also determine the final property of the composite material. Then the orientation. In the left hand side figure, the orientation is straight. Orientation of the dispersed particles are straight. In the right hand side figure, the orientation is little bit tilted. So that orientation will also determine the final properties of the matrix of the composite material. So we have seen there are the concentration. What were the 5 cases which you have seen? The concentration, the size, the shape, distribution, and orientation. All these determine the final properties of the composite material. Now after we discuss the composite materials, let us see what nanocomposites are. So far the composites which we have been discussing, those composites were the macro scale materials, where the sizes are not in the nanoscale. Because we will be discussing on nanocomposites, probably Madam had also discussed nanocomposites in the last session. So these nanocomposites, what actually the nanocomposites are, here also there will be 2 phases, the matrix phase and the dispersed phase. And the dispersed phase or the matrix phase, both taken together, the particles will be in the range of 1 to 100 nanometer. So as I had already explained what the nanoscale is, when the particle sizes are in the scale of 1 to 100 nanometer, our composites are called as nanocomposites. It is the same composite like the macro sized composites which we had just discussed, but the sizes of the particles are in the scale of 1 to 100 nanometer. So these nanocomposites are a suitable alternative to microcomposites. So how much is the micro scale? Nano, we have already said it is 10 to the power minus 9. Just before the nano scale, we had the micro scale. Microelectronics, yeah, 10 to the power minus 6. So, in place of nanocomposites, before we used to have the microcomposites. But nanocomposites are a little bit newer concepts and they are a suitable alternative to microcomposites, and they are reported to be the materials of the 21st century. So the century which we are in, and the combination of properties exhibited by nanocomposites are not found in conventional composites. So whenever nanomaterials are formed, their properties will be highly different from what they exhibit in the macro scale. And one example is copper. Copper, we all know, the material copper is used in our drawing the electrical wires. Okay, the color of copper we all know, it is opaque and color we are familiar with. But at the nano scale, copper becomes totally transparent. That is a huge change of property. Then platinum. Platinum, you know, it is more or less an inert, it does not react so much. But at the nano scale, its reactivity increases highly. Then gold. Gold, the color, you know, the golden color, how it looks like. But at the nano scale, gold turns liquid. It is no more a solid. It turns into a liquid and its color also becomes red. So these are the property change boli je moi koi asu. Ebilak ketaman examples of changes in property. Again, aluminium. You know, aluminium will not get burned so easily. Aluminium is not combustible. But in the nano scale, aluminium becomes a very highly combustible material. So therefore, these nanocomposites also are materials which will show very different properties compared to what they exhibit in the macro scale. The combination of properties exhibited by nanocomposites are not found in conventional composites. I have already said the processing technique of nanocomposites is also very unusual, and nanocomposites can be divided into three categories: ceramic matrix, metal matrix, and polymer matrix based nanocomposites. So if you remember the figures which I had drawn, the pink color portion I had said it was the matrix. So that matrix can be a ceramic, the matrix can be a metal, the matrix can be a polymer also. And we will be discussing on the polymer based matrix materials only here. But then the polymers are not only the matrix materials, the matrix materials can be ceramic, it can be metal, it can be some other material also. Then there are some conducting polymer based nanocomposites which have come into market recently. Again, biodegradable polymer based nanocomposites are also one of the recent achievements. You know, polymers, they do not get degraded so easily. So, biodegradable polymer based nanocomposites. This is also a new field of research and it is a new achievement. Carbon nanotube dispersed polymer matrix composites are also novel materials possessing better toughness and interfacial bonding. So in place of those blue arrows, which I had just used as a representation of some dispersed particles, if you insert carbon nanotubes, that carbon nanotubes may serve as the dispersed phase material. And carbon nanotube dispersed polymer matrix, where the matrix will be a polymer, the dispersed material will be carbon nanotube. This kind of nanocomposites are also novel and they possess better toughness and interfacial bonding. Novel material means they are new kind of materials. Now because we deal with core shell nanocomposites, so the composites in all cases might not be only a mixture of two materials, or it might not be a combination of two materials. The two materials may also be taking a different pattern, which means one material may be in the form of a core, which will be surrounded by the shell of another material. So the composites can also be existing in the form of core shell materials. Now, what is the advantage of core shell composites? When the material is single or when the semiconductor is single, the surface atoms will have less coordination number, which will result in the formation of dangling bonds. So, coordination number, you know, actually the number of atoms to which one single atom is bonded to. That is the coordination number. So, if you have one surface atom, because the atoms are at the surface, it might not be bonded on all sides. The surface atoms, it will have incomplete bond exactly at the surface. Because this side it will have bond, this side it will have bond, underneath it will have bond, but on top of it, the bonding will be incomplete. And those bonds are called as dangling bonds, incomplete bonds. So, it will have less coordination number. So, if the number of bonded atoms are less, we say that the coordination number is less. And non-radiative transitions may occur, resulting in decrease of quantum yield. Now, one of the greatest uses of semiconductors are in their emission field. Semiconductors are highly emissive. Some semiconductors, they can emit radiations very easily, but if the semiconductors have dangling bonds and less coordination number, then that radiative transition may decrease. Radiative transition only results in emission, our light emitting diodes and all. So that radiative transition, if it is less, then the quantum yield will be less, which means the emissive power will be less. So in that case, if there is a layer of one more semiconductor surrounding the first semiconductor, then this may result in reduction of photodegradation, which means there will be less degradation, and it can increase the emission or the fluorescence. Fluorescence is a kind of emission only. And the shell will also provide protection to the core against environmental changes, and it will protect it from degradation. So this is semiconductor core shell nanocomposites, is one kind of composites which we work with. So this is the broad classification area of composites. You see, for composites, I said composites will have a matrix, it will have a dispersed phase. The dispersed phase may be in the form of fibers, it may be in the form of particles. Dispersed phases are also called as reinforced phase. And there are one kind of composites which are also called as structural composites. And these particle reinforced composites, they may be large particle reinforced, or there is a particular category which is called as dispersion strengthened. Again, fiber-based composites, they find application, mostly they find the applications in many areas. The fibers may be continuous or discontinuous. And the structural composite, they may be laminates or sandwich panels. These are specific types. And the discontinuous fibers may be aligned, or they may be randomly oriented. So, because I had discussed the concepts of vehicles, nowadays, আজিকালি এনেকে নকয় নে vehicle bodyবোৰ fibereৰে বনোৱা. It is a commonly going term nowadays. It is not metallic, but it's made of fiber. Then the specs, we say it's fiber based, our lenses. Okay, so this is the fiber reinforced composites are actually finding most of the applications. So whenever we say that something is made of fiber, it is not that it is only fiber, but it is fiber reinforced composite material. Even those tubeless tires nowadays, okay, that rubber is some reinforced rubber which is used, for which the tubeless thing has come into existence. So this is the different areas of our composite materials. So we are mainly concerned with the polymer matrix composites. So these are those composites where a polymer resin is used as a matrix. As I have said, the matrix may be a metal, the matrix may be a polymer, or the matrix may be some ceramic. So polymer matrix composites are those composites where a polymer is used as the matrix with a specific reinforcement material. So these materials are used in the greatest diversity of composite applications, and because of their good properties which they exhibit at room temperature. And it is easy to fabricate such composites, and the fabrication processes are also not very expensive. Now, what are the role or what are the functions which the polymer matrix performs? So, it performs a very important role. It determines the maximum service temperature of the material. So, if a material is polymer based material, that material might not be usable at very high temperature, because most of the polymers gets degraded at high temperature. Therefore, we are saying, because the matrix will be the one which will be facing the external environment, the other particles will be embedded within the matrix. Matrix or bhitorot thakibo. Fiber e hok, particle e hok, ba belek kiba e hok, those will be inside the matrix. Therefore, the matrix will determine the maximum service temperature. So, kiba jodi gorom environment face kore, matrix to face koribo first. So, it might not be usable at very high temperature, because the polymers normally softens, melts or degrades at much lower temperature than the corresponding reinforcement. And the most widely utilized and least expensive polymer resins are polyesters and vinyl esters. Like in the commercial market, the polymer based materials which we are using, the main resins which are used are polyesters and vinyl esters, which are commonly used in glass fiber reinforced composites. Then there is one more kind of polymers which are called as the epoxies. These are most expensive polymers, and in addition to commercial application, they are also utilized in aerospace applications due to their better mechanical properties and resistance to moisture in comparison to polyesters and vinyl esters. So this epoxy jodi matrix hisabe use kore, then it will be resistant to moisture compared to the polyester or the vinyl ester. And for high temperature application, these polyimide resins are also used as the matrix. And there are some other polymers like high temperature thermoplastic resins. It possesses potential to be used in future aerospace applications. Such materials are polyether ketone, PEEK it is said, then polyphenylene sulfide and polyetheramide. These are some polymers which can be used at high temperature also. Now, this is something which all of you might be knowing what a polymer is. So, it is a class of material which is composed of fairly large number of repeating units. So, it is called as, the repeating units are monomers. And polymers constitutes many of the materials in living organisms. It is not that polymers are all artificially made. Some natural polymers are also there. And in the human body also, we have proteins and all. So, the cellulose, nucleic acid, all these are natural polymers. Plastic rubbers are synthetic polymers. And in this figure, I have just shown a polymer chain, and the corresponding that chain along with the monomer is also shown below. So, in our nanosynthesis, how does the polymer help us? Okay, so polymer, we always use the polymer as a matrix material because it will help our nanoparticles to get not to get converted to the macromolecules or the macroform. Okay, so when the nanoparticles are formed, if it is embedded within the polymer matrix, then the nanoparticles will not remain in contact with one another because the matrix material will be in between the nanoparticles. The nanoparticles will be surrounded by the matrix material. So, because the two nanoparticles will not come in contact with one another, it will prevent the agglomeration of nanoparticles. Okay, so that's why we use our different kinds of polymers in our work. These polymers are used as matrix material. So before I start discussing our work, if you have anything to ask, you can ask me. Okay, so কিবা সুধিব বিচাৰিলে সুধিব পাৰে. So I said we fabricate or we synthesize nanoparticles or nanocomposites in our lab. So different polymers which we have been using as the matrix material are listed here. Polyvinyl alcohol is one. In short, we call it as PVA. Then another is PVP, that is polyvinyl pyrrolidone. Then another is PANI, that is polyaniline. And we have so far synthesized different nanoparticles and nanocomposites. You see, when the PVA and CDS is one, CDS is cadmium sulfide, PVA zinc sulfide is one, then PVA CDS ZNS. So there is two different nanoparticles there. So it is a nanocomposite. Then PVA ZNS ZNO, then PVP ZNS PVP ZNO. ZNO is zinc oxide. Then PANI CDS ZNS, and PVA ZNS titanium. These are different nanocomposites which we synthesize in our lab. Now here let us see what polyvinyl alcohol is. It is denoted as PVOH or PVA. It is water soluble synthetic polymer, and vinyl acetate is the monomer. And it has a formula CH2CHOH with n number of repeating units. And it finds application in paper making, textile wrapping, then thickener and emulsion stabilizer in different coatings and in 3D printing. Then it is water soluble and it is colorless and odorless. The melting point is 200 degrees centigrade, boiling point is 340 degrees centigrade. It is having a density of 1.19 gram per centimeter cube. These are all different information regarding polyvinyl alcohol or PVA which I have collected. There may be many other information also. Now polyvinyl pyrrolidone, that is one more matrix material which we use. That is also water soluble polymer, and it is made from monomer and vinyl pyrrolidone, and it's C6H9NO with n number of repeating units. It is available in a range of molecular weights and related viscosities. The melting point is 150 degrees centigrade. Molar mass is 2500 to 500,000 gram per mole. Then its density is 1.2 gram per centimeter cube. Appearance is white to light yellow, and the formula is C6H9. I have already written it. Then it finds use as binder in many pharmaceutical tablets. And when added to iodine, it forms a complex called providine iodine that possesses disinfectant properties. This iodine solution is widely used in treatments, and it helps in drying of wounds actually. The PVP is also used as lubricant in some eye drops. It is also used in some contact lenses and their packaging solution, and it has a host of other applications. This is polyaniline. It is actually a conducting polymer. The PVA and PVP are non-conducting, but PANI or polyaniline is a conducting polymer and an organic semiconductor. It is organic semiconductor actually. So it belongs to flexible rod polymer family and possesses improved electrical conductivity and mechanical properties. And it is formed by polymerization of aniline, which is C6H5NH2. And it has three different forms which I have listed here. That is leucoemeraldine, which is white and clear in appearance. Then pernigraninine, blue violet in appearance, and emeraldine, this green blue in appearance. And it is one of the most widely studied conducting polymers. There are not many reported works on conducting polymers, but recently the number of work performed with conducting polymers has increased. So after that, as I had said, I will discuss what the compound semiconductors are. Somewhere I had written 2,6. Okay, so I have included one slide regarding that. So you know that at the starting of electronics industry, silicon was the main semiconducting material which was used, and along with silicon, germanium was also widely used.
Can I have that with the funny slide?
So along with silicon, germanium was also used in electronics industry for different semiconducting performances, mainly the wafer of the integrated circuit it was used. So can I move now? So like few years back, silicon along with germanium were the main semiconducting material which were used in the electronics industry. And it was observed that semiconductors which are formed by ionic bond of multiple kinds of semiconductors are called as compound semiconductors. So there may be semiconductors which are not single, but they are compound. We don't call them composite, but they are compound semiconductors where there will be ionic bonding of multiple kinds of semiconductors. So two or more than two semiconductors taken together will result in the formation of a compound semiconductors. Therefore, materials formed by ionic bonds become insulators because of their strong electrostatic force of attraction. Normally, when there is ionic bond between two materials, because ionic bond is very difficult to break, the material becomes insulator. But it has been observed that in many cases, the material possesses semiconducting behavior also, and with a particular combination of the two materials. Okay, so with particular combination of two materials, you may form compound semiconductors. So here I have shown a portion of the periodic table where there are different groups and the elements which are present under those groups. So you have different kinds of compound semiconductors that has been used in making various devices, and they are also available commercially. So widely known groups of compound semiconductors are 3, 5, 2, 6, 4, 4, like that. Like you take two elements from two different groups of the periodic table. So the semiconductor name will go along with the group name. When you take cadmium sulfide, cadmium belongs to one group, sulfide belongs to another group. So cadmium, where is cadmium listed? It is under group 2, and our sulfur is in group 6. So cadmium sulfide will be a group 2,6 semiconductor. Similarly will be the case with zinc sulfide. Zinc is under 2 and our sulfur is under 6. So zinc sulfide will be a 2,6 semiconductor. But zinc sulfide, cadmium sulfide, those we are working with because our labs are equipped with those kind of facilities. But actually the compound semiconductors which are finding most of the applications are gallium arsenide. Gallium arsenide namtu sage sobe shunise. Gallium arsenide is a very important material. This is a compound semiconductor where gallium is belonging to group 3 and then arsenic is belonging to group 5. Then indium phosphide, gallium nitride, aluminum nitride, all these are well known 2644 semiconductors. Then there are other compound semiconductors also like zinc selenide, then zinc sulfide, cadmium, telluride, silicon carbide, silicon germanium. Both of them also form a compound semiconductor. Okay. Then these are some frequently used compound semiconductors. So I think there is some repetition of words. The sentence is ending at respectively. This one extra word that bhulote annual second. So I hope what compound semiconductor is you are able to follow. So in our work, we synthesize compound semiconductors, and those compound semiconductors, for example, cadmium sulfide, zinc oxide, lead sulfide, those are embedded in different polymer matrices like PVA, PANI, or the PVP, all those. And we take some specific method for synthesizing, and after synthesizing, we characterize them with different characterization technique. So far, we have used this characterization technique, the UV visible spectroscopy, photoluminescence spectroscopy, X-ray diffraction, scanning electron microscopy, then energy dispersive analysis of X-rays, transmission electron microscopy. All these techniques we have used. So I am not going into the details of these techniques, only the names I have mentioned. So here I start showing some of our results. Okay, so this is PVA capped zinc sulfide nanoparticles varying PVA concentration. This is one work which one of my student had performed. So here the amount of PVA, you see, we have prepared 4 different samples, S1, S2, S3 and S4, where the PVA concentration was changed at a specific interval, 0.25, 0.5, 0.75 and 1. And these zinc chloride and sodium sulfide are what? They are the reacting materials. By the reaction between zinc chloride and sodium sulfide, we get zinc sulfide nanoparticles. So in the 4 different figures which I have shown here, these are UV visible spectra. In the UV visible spectra, we get an idea of the position of absorption edge and the band gap of the material. Now what is absorption edge? Actually, when electromagnetic radiation is passed through any material, maybe solid, liquid, any material, it will absorb some amount of the radiation, and the amount of absorption will change with the change in wavelength of the electromagnetic radiation. Now that absorption will suddenly take a turn, or it will suddenly increase abruptly at a point. That point is called as the absorption edge. That absorption edge is actually associated with the band gap of the material, and from the absorption edge wavelength we can calculate the band gap of the material. So if the material is a nanomaterial, the absorption edge will be at a shorter wavelength compared to the bulk nanomaterial. So looking at the absorption edge, if at the very beginning you find that the absorption edge is at a shorter wavelength compared to the bulk material, you get a confirmation that a nanomaterial has been formed. Okay, so the absorption edge in this case has observing it at a shorter wavelength is called as blue shifting. So at this case there is blue shifting of the absorption edge. You see, I have given that table for the 4 different samples, S1, S2, S3 and S4. We had observed the absorption edges from the 4 graphs which I had shown in the last slide, and we have seen that with increase in the PVA concentration, the absorption edges were shifting towards the shorter wavelength, which in other words will mean that the absorption edges are shifting because the particle sizes are decreasing. So the amount of PVA, when we are increasing, it is helping in getting the particles become smaller in size, or in reduction of the particle size, it is helping us. So it is actually more quantum confinement which is occurring, which is resulting in the decrease of particle size of the material. So this study actually had shown that for this particular material only, then with increase of PVA concentration, we get lesser particle sizes for the zinc sulfide nanoparticles. Now that is the PL spectra. Okay, so PL actually it gives us information about the emission of the particles. So when electrons jump, because it is a semiconductor.
Bandage emission and absorption.
absorption, edge and bandage. Okay, I'm telling that absorption actually is how much radiation is absorbed by the material. That absorbance is how much it has absorbed, and that absorbance will change with change of wavelength. So when you are constantly changing the wavelength, the pattern will keep on changing, or like it will actually we start from the longer wavelength and come towards the shorter wavelength while taking the data. So it is taking one path and suddenly it is increasing at one point. That increasing, wherever it is increasing, we call it as the absorption edge. But emission actually is because it is a semiconductor. So there is a conduction band and a valence band, and when electromagnetic radiation is incident upon the material or the semiconducting material, then the electrons which are at the valence band, they will gain energy to move to the conduction band, and at the conduction band again they will be in an unstable state, and they will again try to jump back to the valence band again. So if they jump from the conduction band to the valence band, they will emit some radiation. That is called as the PL, photoluminescence. Depending upon the time it takes to emit, the phenomena will be either called as luminescence or fluorescence. Now both are similar phenomena, only the time of occurrence is different for the two cases. Now when this first peak which comes, you see for all the samples there is one first peak at the left side. That is called as the band edge emission, because the electrons will jump throughout the band. Okay, it will jump মানে কি তোমার কন্ডাকশন ব্যান্ডৰ পৰা ভ্যালেন্স ব্যান্ডলৈ হি জাম্প কৰিব, হি তাৰমানে গোটেই ব্যান্ড গেপটো কভাৰ কৰিছে, সেইকাৰণে ব্যান্ড এজ এমিশন means it is jumping from the edge of the conduction band. Conduction bandৰ এটা upper level থাকে, এটা lower level থাকে, আকৌ ভ্যালেন্স ব্যান্ডৰো এটা upper state থাকিব, এটা lower state থাকিব। সেই conduction bandৰ যোনটো lower edge, হেতুৰ পৰা ভ্যালেন্স ব্যান্ডৰ যোনটো upper edge, edge মানে side আৰু সেই দুটাৰ মাজত যোনটো ট্ৰানজিশন হ'ব হেতু band edge emission বুলি কয়। কেতিয়াবা গোটেই band gapটো কভাৰ নকৰিবও পাৰে, কৰবাত মাজতে আহি ডিফেক্ট ষ্টেট এটালে ঘূৰি আহিব পাৰে ইলেক্ট্ৰনটো।
coming from PL spectrum.
Yeah, this data is coming from the PL spectrum, that band edge emission. So here PL spectrum যে প্ৰথম যোনটো peak আছে হেতু band edge emissionৰ peak, কিন্তু পিছলে আকৌ কেনেমান খুব ইমান স্পষ্ট নহয়, কিছুমান peak আহিছে, সেইবিলাক তাৰমানে ইলেক্ট্ৰনবোৰ গোটেই band gapটো জাম্প কৰা নাই, তাৰমানে কৰবাত মাজতে আহি ডিফেক্ট ষ্টেট এটা ৰৈ গৈছে, তেনেকুৱা যদি থাকে we call it as defect level emission. So whenever it is covering the whole band gap, we call it as the band edge emission. Okay, so these results I have already listed here. The absorption edges are blue shifted with increase in concentration of PVA. So from that we know that sizes of the nanoparticles are getting reduced with increase in PVA concentration, and effect of quantum confinement increases with increase in PVA concentration, and position of band edge emission also gets blue shifted with PVA concentration. See S1 S2 কারণে একে আছে 324 তে আছে, কিন্তু S3 S4 এর কারণে অকমান শিফট হল shorter wavelength তলে, 1 nanometer difference is there. So we say that it is blue shifted with increase in PVA concentration. Okay, is there anything you'd like to ask?
And here same excitation was applied for PL.
So actually for PL and UV, the excitation wavelengths are a little bit different.
And for different PL spectra.
Oh yeah, it is same. When taking the PL spectra, because S1, S2, S3, S4 are all the same material, only matrix concentration is different, so the excitation wavelengths were same. And the spectra are coming, different spectra we are getting. Okay.
And that second hum maybe for second harmonic generation.
Those other peak. defect level emission সেইটোৱে
impurities
থাকিব যদি হেকিটা এমিশন না থাকে তেতিয়াহলে ক্রিস্টাল স্ট্রাকচাৰটো ভাল আৰু এইটা না থাকিব মই তেনেকুৱা দেখুৱাম আৰু আছে আমাৰ So this work was performed by Rijwana. She is sitting here. So this has been accepted in one of the journal. So here also we have changed the concentration of PVA and we have synthesized different samples of CSTS-GUWAHATI in core shell structure, whereas the cadmium sulfide was the core and zinc sulfide was the shell material. You see this cadmium chloride, sodium sulfide, zinc chloride, all these are the reacting material or the precursor material, and the PVA concentration we have changed in equal interval. And at that corner all the UV patterns are shown, and it is observed that the absorption edge of the CDS core sample was blue shifted compared to bulk. যে এটো হলে প্রথম অবজারভেশন আমি চাব লাগিব যে বাল্কতকে তার absorption edge to blue shifted হৈছে নে নাই বাল্কৰ ভ্যালু টু 512 আৰু বিআর ভ্যালু আহিছে more or less at 322.3 nanometer. So we are saying that all the absorption edges are blue shifted, and this is an indication that nanoparticles have been formed. Then the absorption edges of the core shell materials are slightly red shifted. Now once you deposit the shell over the core material, the particle size again increases. Particle size increase হওয়ার কারণে কি হয় that the absorption edge is again red shifted in comparison to the core material. So this is due to the deposition of the shell over the core, which increases the particle size. Then absorption edges of all the core shell samples are more or less situated at the same position. So absorption edges of core shell samples. So C6, this 6-7 code are given because there was one more set where PVA was not varied, something else was varied. This 6-7, 8-9-10, these are second set of samples. So the numbers are going like that. So if you see for CZ6, CZ7, CZ8, CZ9, all the absorption edges are more or less at the same position with only difference in decimal point. Okay, so we are saying that for the core shell samples, all the absorption edge are more or less located at the same position. And this means that with increase of PVA concentration, the particle size remains more or less same. So in case of zinc sulfide single, we have observed one kind of result. In case of CSTS-GUWAHATI composite material, we are observing another type of result. So the cases are material specific actually. So here the PL spectra are more or less defect free. Okay, because only the bandage emission has come. Now the peak corresponding to bandage emission was found to be red shifted for the core shell sample as compared to the core. And the sample with maximum PVA concentration showed the maximum intensity, which means the one having more maximum PVA concentration, that was the one having more emission. And for sample CZ7, there is a shoulder that is actually those below the ওপৰৰ কিটা নহয় তলৰ ফালে থকা কাৰ্ভ কিটাৰ পৰা আমি কৈছো that for sample CZ7, a shoulder is observed in the range 422 nanometer to 441 nanometer, which may be due to the emission from defect or vacancy stain within the crystal. In the rest of the sample other than core, no other emissions were observed except the bandage emission, which indicates formation of good crystal structure. So in one case I have discussed only a single nanoparticle zinc sulfide embedded in PVA. In this second case we have a composite nanomaterial, that is CDS and ZNS, embedded in PVA. In both cases PVA was the matrix. So for this sample we also have XRD results. Okay, so maybe this is coming very small, but diffraction peaks which will come, and the diffraction peaks we will have to match with some standard data or some standard position for diffraction peak which are given by a standard data called JCPDS file. So if that these peak positions which matches with those given by the JCPDS file with some specific number, then we can confirm that the material has been formed correctly. So for CDS core, we had observed diffraction peaks at 2 theta equal to 26.4, 43.9, 52.4, then 70.0, 70.8, and these are corresponding to different places like 111, 220, 311, 420. I don't know you are familiar with these or not. These are called as Miller indices. Because in the hexadecimal terminal our key hoy crystal or beleg plane thake x-ray so ami juntu sample prepare koru ei sample tur through ami x-ray radiation pass koru in the x-ray hexad experiment pass korile crystal or beleg plane or pora beleg angle reflect hobo ei x-ray beam to hey reflection angle bor ami standard value etar logot compare koribo lage standard value bor kune diye that JCPDS data so JCPDS data koi dise bole a2 angle or pora jodi reflection ahe tetia hole a2 planar hobo lagibo ba jodi bole 2 theta equal to 26.4 boli likhisu hetur pora jodi diffracted hoy beam to then it will correspond to 111 plane. Again 43.9 from there if it is diffracted then it will correspond to 220 plane. Teneke ami JCPDS data logot match kori uliabo lagibo je amar juntu pattern to form hoise ei uporor prothom tu figure juntu pattern paisu that pattern is corresponding to the standard pattern or not. Jodi standard pattern logot match hoise exactly match no hobo pare 1-2 degree ifal thakibo pare kintu maximum match hole amar material to hoa boli ami gom paam. Again when there is a composite material like in the second figure we have CDS ZNS, then there will be peaks corresponding to both the material. There will be peaks corresponding to CDS also, there will be peaks corresponding to ZNS also. So you have to match your figure with both CDS and ZNS JCPDS file, and then you have to find which peak is for CDS, which peak is for ZNS. Okay, but when the amount of ZNS is very less, peaks for ZNS might not come. Jodi etia ami amount to bahai di shellor amount ketiaba bahai dibo paru concentration to tetia tar peak bilak distinctly ahe. So here আমি বড় difference observe করা নাই কিন্তু অকমান ZNS or influence to আছে salient graph pattern of. Then third pattern too, it is the XRD pattern of only ZNS. Okay, ZNS or bole kuntu angle of plane form hoy there we have compared with the JCPDS file of ZNS. Now there is a formula which is called as the device error formula, with the help of which you can calculate the sizes of the crystals. It is called as average crystallite size. Those have also been calculated and it has been found to be 3.5 nanometer for CDS, then 2.9 nanometer for ZNS shell and almost 5.5 nanometer for the CDS ZNS core shell nanoparticles. See, just to give you an example of how the SEM images look like, I have inserted these two figures. These are SEM images of the samples. The first one on the left is of CDS and on the right that one is of ZNS. Okay, so this is one more word. Here we have used PVP, polyvinyl pyrrolidone, and this work was performed by PVP2. So here you see আমি PVP এমাউন্টটো চেঞ্জ কৰা নাই কিন্তু আমি চেঞ্জ কৰিছো ৰিঅ্যাকশন টাইম যেতিয়া আমাৰ গুটেইবিলাক কেমিক্যাল মিক্স কৰি হৈ যায় when we have inserted all the precursor material the final time the material takes to form that is called as the reaction time material form hoto ami keneke gom paum jetia ami bole zinc acetate dilu sodium sulfide dilu dutar majot reaction hol reaction hoy eta color change ahibo he color change to dekha pale ami gom pao je amar required material to form hoise ne nai je zinc sulfide form hoise ne nai so he reaction time to ami change kori saisu je amar UV and PL data ami kenekwa heri paum changes paum with the change of reaction time so these all are the UV curve this work was performed by one of my student Mriganka Mohanto he had come from Kaziranga University so this is UV VIS and PL spectra of the samples okay and here are
magnetic stand
for magnetic stand through magnetic staining only we have done all these samples so we sample code pisu ZS1 ZS2 ZS3 ZS4 ZS5 and reaction time was our how much time is left 1 hour 1.5 hour 2 hour 2.5 hour 3 hours like that so there was no specific pattern in the shifting of the absorption edges at first it was red shifted jetia longer wavelength or phale jay ami red shifting boli kom aru jetia bole ako shorter wavelength le ahe ami ta blue shifting boli kom to ebar dekhilo red shifting hol pelai ako blue shifting hoise so corresponding band gap pilako ami ulialu eta formula ase Gauss formula boli koy hetu use kori ami band gap uliabo paru okay so the position of the absorption edges initially gets red not red it was red shifted to 30 or more initially gets red shifted with increase in reaction time and then gets blue shifted with further increase in reaction time and the band edge emissions are all located at the same portion except for ZS5 which is slightly red shifted so band edge emission which is emission across the band gap gutei ita ekata wavelength te ase okol eta okoman red shifting ase so PL value to dekhoise ne PL to tat ase screen khon aru damor ke ulabo boli bhabisilu moi so okoman horuke ahise ina that last one is the PL spectra so this is one more sample that is PVL ZNO something I missed PVP ZNS2 kolu hai PVP ZNS2 kosu PVP ZNO this was performed by one more student from Kaziranga University like their PG dissertation work they had done so here our ZNO nanoparticles were embedded in PVP matrix and here also we had changed the reaction time and the different UV visible spectra are shown and also the PL spectra are shown so let us see the result so all the absorption edges you see it was initially at 238 then shifted to 237 36 protomote komi ahil tarpor ako olopman bari gol komi jwa mane particle size komi se aru tumar bari jwa mane ako particle size bari hoise so exciting emission again it is 291.5 all are located at the same position but there was one difference that is the values of intensity to kisumanor karone beshi kisumanor karone kom atakke beshi ami palu 1222 that was for the second sample with a reaction time ration time to dekhwaisu last slide that was 90 minutes. So again this work was performed by my student Jasmine Sikdar. Okay, this is her postgraduate dissertation work. This is also accepted for publication in a journal. Now here we had synthesized zinc oxide, zinc sulfide nanocomposites, and we had changed the molar ratio between zinc oxide and zinc sulfide. So our list of samples are given here. We have S1, S2, S3. S1 is only zinc oxide, S2 is zinc oxide, zinc sulfide with 0.1 molar and 0.2 molar amounts of the two samples, and S3 is 0.2 molar and 0.2 molar. Okay, so our absorption edges are, see, for the core sample it was 338 nanometer, but for the core shell sample it was highly redshifted at 370 nanometer for both the cases. So all these spectra are shown here. The PL spectra is also shown here, and the XRD images or XRD patterns of all the three samples are shown. In the top figure, it is the XRD pattern of the single zinc oxide. All the planes which are, or the peaks which are occurring here are corresponding to different planes of zinc oxide alone. But in the second, that light blue figure or curve, there you have planes corresponding to both zinc oxide and zinc sulfide. But the contribution of zinc sulfide is less here because the amount of zinc sulfide was less there. So peaks of zinc sulfide were very less intense in this case. But in the second case, the peaks of zinc sulfide were more intense because the amount of zinc sulfide was more there. So this was one observation we had done with zinc oxide, zinc sulfide nanoparticles. Okay, so this was again done by the same student, Jasmine Sikdar. Here we have changed the position of the core and the shell. This is zinc sulfide, zinc oxide, and embedded in PVA matrix. So you see we had prepared S4, S5, S6, S7, and S8 is the core sample. We have compared the position of the absorption edges. All the absorption edges were blue shifted compared to the bulk material, and these are all the UV spectra. So it was 330 nanometer, 335, 333, 332. Little bit of red shifting is also there. The absorption edges of the core shell samples. Core shell samples will be red shifted only because the sizes of the particle becomes larger when the shell is deposited. So when the sizes are small, there will be blue shifting. When the sizes are more, there will be red shifting. And the PL spectra is shown there, and on the top left corner, and our XRD pattern for zinc sulfide is on the top right corner. And for all the four shell samples, the XRD patterns are shown below. So what we have observed, the PL spectra shows that emission intensity of zinc sulfide is greater than zinc sulfide zinc oxide. So deposition of the shell has lowered the emission intensity in this case. And amongst all the three zinc sulfide zinc oxide samples, the emission intensity of S6 is lesser compared to S4, S5, S7, all of which possess almost the same intensity. And the emission wavelength of zinc sulfide, zinc oxide are redshifted compared to zinc sulfide. And XRD spectra, it should be pattern. XRD pattern also shows presence of crystal planes due to both zinc sulfide and zinc oxide. So when there is a core shell or composite sample, the planes of both the materials will be visible. And with the deposition of zinc oxide shell over zinc sulfide core, the dominant 111 peak of zinc oxide gets suppressed, and it's that more intense 111 peak which is shown there on the right hand side. When the shell was deposited, that peak got suppressed or became lesser in intensity, and that intensity decrease was more intensified when the amount of shell precursor was increased, or concentration of shell was increased. So the device error formula, I had already said that there is a formula to calculate the crystal sizes. So that is D equal to K lambda by beta cos theta. That is the formula. Using that equation, we have calculated the average crystallite sizes of all the samples, and the different sizes are listed here. Okay, so just to show you some of our images, this is again from Rejoina's work. There are some rods type samples were formed in the same work which I had discussed before, CSTS nanoparticles. And there is something called histogram, which can show us particle size distribution. These blue bars, okay, are from the SAM images and also from the TAM images. You can draw histograms. The more longer or the more height one will show that the maximum particles are located along that particular size scale. And you see the TAM images that was taken in Nehu Shillong, the lattice fringes. Crystalot ki thake, crystalot he planes bilak thake boli koisilu nohoy, he planes bilak yat visible hoise. Eneka line je asas para nisna ase je, those are the crystal planes. Okay, so from these different planes only we get the XRD patterns which are formed as in the form of peak. Now what SAM EDX data gives us, it gives us the composition of different elements in the sample. So SAM EDX spectra of CDS, that is from her work that I have shown here. So how much amount of different samples or the materials are found in the sample, that can be seen from here. Okay, so these are the different references which I had used in preparing the general portion and in also the different results which I have shown here. And I thank my students, their work I have shown here. Sultana Rejoina Haq, then Rajit Nath, Viranka Mohanto and Jasmine Sikdar, whose work I have discussed here. Then I am thankful to SAFE, Department of Instrumentation and UC, Guwahati University, for the XRD results, and to Department of Chemistry, Guwahati University, for the SAM micrograph, and SAFE Nehu Shillong for TAM HR10 analysis of the samples. The UV and PL spectra were measured in Department of Applied Sciences itself, and I am thankful to Digital India Corporation, Ministry of Electronics and Information Technology, for granting me the Young Faculty Research Fellowship. And this work was done with that funding, and I'm thankful to them. If there is anything you can ask.
Ma'am, generally আমি এটো এটা ফরওয়ার্ড ডাইরেকশন আমি স্টাডি কৰি আছো। সাপোজ ফার্স্টতে আমি সিনথেসাইজ কৰিছো মেটেৰিয়েলটো নেনো ফৰ্মেশনে চাইছো XRD SAM TAM এনেকৈ লৈ লৈছো। তাৰ পিছত তাৰ বিভিন্ন আপোনাৰ প্ৰপাৰ্টিজ বিলাক চাইছো। সো এটা যে মোক ৰিভাৰ্সত লাগে, সাপোজ মোৰ এটা স্পেসিফিক ওয়ার্ক আছে, সাপোজ সেই ওয়ার্কটোৰ কাৰণে কি ফান্ডামেন্টাল প্ৰপাৰ্টিজ লাগে এইখিনি চালো। তাৰ ৰেসপেক্টত আমি how can we approach to that project? We need something specific to build actually.
You know the application and which material you will use.
Yeah.
So in that case, to study kori labo lagibo material or beleg property. You have to make a literature survey actually. Literature survey kori tumi sabo lagibo je kuntu material e kenka property tumar exhibit kore.
Because we need to make the composite material, not a single kind of product.
So you need to study that also. Everything might not be available in literature also. So maybe you have to synthesize and see what property it is exhibiting. So from literature you may get some help, or if you don't get, then you have to for the individual material you have to study its property. Then you have to see that if I make a composite out of it, how can those properties get changed? Because as I said, in a composite, each of the material will have its role. Final property to protitu material or property sum. It is a sum of properties of all the materials. So in that case, you will have to take some chance and you have to prepare on your own the composite, and then you see that you need to বিচাৰিছা হৈছে নে নাই. In case it is approaching to some extent but not perfectly, then you can do that tuning what I say. You change the amount of proportion, your dispersed phase or amount to change কৰিব পাৰা, আৰু বেলেগ কিবা parameter change কৰিব পাৰা, কৰি যেতিয়া তোমাৰ মানে যোনটো লাগে আহি গল, তেতিয়া তোমাৰ application to possible হ'ব.
Suppose আমি জানো এটা solar voltaic cell or efficiency একদম কম 20% বা maximum 25%. So if we build some material which is used in photovoltaic cell, so we need efficiency high, we need that resistance, we need that efficiency. So how can we approach those material which are more efficient in that particular segment? So suppose efficiency বঢ়াবৰ কাৰণে suppose আমাক resistance বেছি হ'ব লাগে, বা আপোনাৰ যেটোৱে আপোনাৰ যেনেকুৱা material লাগে য'ত মানে আমাৰ solar radiation to basically absorb কৰিব, তেনেকুৱা material লাগে. So আমি তেনেকুৱা material বহুত কেইটা আছে. So which one we can use, or if we use heat and trial method like that or something like that?
Heat and trial to some extent you have to do.
Okay.
Karon tumi
it will take long time. Is also one thing.
Research will take time. Research to eta one day matter to no to time লাগিব. গতিকে তুমি কমানটো চাই লব লাগিব, মানে এতিয়ালৈকে ৰিপৰ্টেড ৱৰ্কত কেনেকুৱা মেটেৰিয়েল ইউজ হৈছে বা কেনেকুৱা এফিচিয়েন্সি দেখুৱাইছে, তুমি তাতকে বেলেগ কোনটো মেটেৰিয়েলে আৰু ভাল এফিচিয়েন্সি দেখুৱাব পাৰে, গোটেই মেটেৰিয়েল প্ৰপাৰ্টি তুমি ষ্টাডি কৰিব লাগিব, বাট ৰিচাৰ্চত তুমি টাইম দিবই লাগিব. পটককৈ এদিন চালোঁ এইখিনি বিচাৰি পালোঁ আৰম্ভ কৰিলোঁ তেনেকুৱা নহয়, লিটাৰেচাৰ ষ্টাডি কৰিবই লাগিব. So you have to make a list that this so and so has performed this work, has got this result, and after that this particular group had enhanced that result, and then after that this particular material was changed by this amount by some other group. So now what I can do, তেনেকুৱা ধৰণৰ কৰি ল'ব লাগিব এটা ষ্টাডি কৰি পেলাই তুমি মেটেৰিয়েলটো এটাটো উলিয়াব লাগিব বাছি পেলাই নিজে. তাৰপিছত যদি ছেটিছফেক্টৰী ৰিজাল্ট নাহে, সেই মেটেৰিয়েলটো এৰি দিব নালাগে, তাক ৰিজাল্টটো কেনেকৈ বেটাৰ কৰিবা সেইটো চাবা. সেই বেটাৰ কৰাটো মেবি এটা চিন্থেচিছ লেভেল অনলি ইট উইল বি পচিবল. চিন্থেচিছত তুমি এনেকুৱা কিবা চেঞ্জ কৰিব লাগিব যাৰ কাৰণে বোলে ফাইনেল ৰিজাল্টখিনি ভাল হ'ব পাৰে. So some amount of time you will have to give in doing the literature study.
Thank you, ma'am.
Thank you, madam. I, on behalf of CSTS-GUWAHATI, thank you for giving this informative session. Thank you. So after a little break, we will go for the laboratory visits, practical session. So we will show the laboratories. Thank you. अभी थोड़ा लैब विजिट करना है. And you come regularly. No? You should come regularly. You have no problem. No, it is not so far also. Isn't it? At least for attendance. No, you come to
যদি দিয়ে তেতিয়াহলে ল'ব
Saturday ko
যোৱা আমাৰ তাত নিদিলে
Saturday ko problem नहीं Saturday ko मुश्किल करेंगे
खुली दिया पाएगा लागे आरो कितना परसेंट हो 18 कितना परसेंट लगभग एसटी डॉक्टर
प्रथम क्लास में गए
जिसके बुरा खुली लगना खुली लगना
और एक दूसरा
এইবাৰ